I'm very happy to have everyone here with us today. We'll move on to the second speaker, who's Ian Fenty, who received his PhD in climate physics and chemistry from MIT in 2010 and now works at NASA's Jet Propulsion Laboratory as a climate scientist. His research includes reconstructing the past 25 years of the circulation of Earth's oceans and understanding how ocean warming is contributing to the melting of the Greenland ice sheet. In addition, he's the co-investigator of NASA's Oceans Melting Greenland mission. And today he'll be talking about future climate change, polar ice melting tipping points, and sea level rise. Prevention is the best cure. Ian?
Oh yeah, I've already violating my instructions. Thank you very much for inviting me to give a talk. It's nice to be here today, beautiful space. It's also nice to see some faces from other talks I've given. I see some folks from the League of Women's Voters, of course, and the Sierra Club and the Citizens Climate Lobby. So I've had the pleasure of meeting some of you and speaking some of your other events. Anne-Marie gave an excellent talk, a great overview of the role of carbon and greenhouse gases in our climate. So it helps me get right to what I want to talk about, which is more about the future of climate change. And let's jump right in. What will determine the future of climate change on Earth? So this is in my opinion, there are three factors. Greenhouse gas emissions from human activity, that's obvious, okay? Natural feedbacks in the climate system, that's less obvious because fewer people know about those feedbacks. And finally, the idea of greenhouse gas removal and storage and geoengineering, which is a topic that was just mentioned at the very end in Anne-Marie's talk and in the Q&A. Of these topics, I will speak about the geoengineering the least. Spend more time about the natural feedbacks to the climate system. So let's get into it. For context, let's look at what has happened already to the climate system since the beginning of the industrial era. So a lot of the figures that I'll be showing come directly from the most recent report from the Intergovernmental Panel of Climate Change, the IPCC report. Now, most of you here have probably heard about the IPCC and know that every few years they release an updated set of reports about consensus documents on the state of climate change. What I want you to do, though, in case you haven't gone to that website in a while, I want you to go to that website because it's actually really, really good. They have made, their audience ultimately is policymakers, right? Which means that they're talking at a level that even our representatives can understand. And it's very clear. It's very clear, very good figures, very good backup, and all the references you want. It's a great starting point, okay? I'm just going to be touching on the highest level of what's in the document. I encourage you all to go. So here are 4 panels. Top left panel is a map showing where and by how much global surface temperatures have changed. And it's very hard to see. I apologize for the sun. But it's about, on average, 2.2 degrees Fahrenheit, okay? And we see, one of the features you see on this map is amplified warming at the poles. And that'll be a topic that we'll get into more later. Steady increase of surface temperatures. This is an average over the globe, okay, from 1880 until today. A lot of variability in the early part of the first 100 years of the record, and then in the last 100 years, a pretty steady increase. Now, in the bottom left panel is something that we didn't talk about in Anne-Marie's talk. This is the extent of Arctic sea ice. This is an annual average, but in this wintertime, the sea ice pretty much is unchanged. It's gone down a little bit, but the biggest changes in sea ice are in the summer. So we have another great reconstruction from about 1880, and we see from 1960 or so on a steady decrease. We'll talk more about that in a little bit also. Simultaneously, we have an increase in global mean sea levels, 20 centimeters or so over the last century. And what's not apparent on this graph is that sea level rise is actually accelerating. So in this graph, we see what looks like kind of a straight line, but in fact, it's been accelerating. That's something else that we'll talk about a little bit later. So there are so many ways that climate change has affected the planet. Here are just four, right? There's four high-level ones. I'm an oceanographer by training, and it's important, to mention that actually the most of the warming, of global warming, happens to the ocean. The ocean makes up about 70% of the surface of the planet. There's huge circulations in the ocean. Colder water comes up from below, interacts with the atmosphere, warms up, and then goes back down again. So the ocean is a huge sink of heat, not just of carbon, as Anne-Marie mentioned. It actually, as Anne-Marie mentioned, carbon dioxide is actually dissolved into the water and taken to great depths. But it's also a great absorber of heat. So in fact, more than 90% of the heat of global warming goes into the ocean. If the oceans weren't around, we'd already all be dead. We would, just like Anne-Marie was saying, if it wasn't for the land and the ocean taking in carbon, the levels of carbon dioxide in the atmosphere would already be much higher. Right? But if it wasn't for the ocean actually taking up some of that excess trapped heat, we'd already all be dead too. So this is my, nod to the fact that we live on land, but you don't have to do very much to Google Earth to just realize that, it's actually mostly we live on an ocean planet, right? And scientists go out into the ocean. We collect measurements about the ocean temperatures. We can do this, it was much more difficult before we had robots and other great technology to take these measurements, but this is a reconstruction from 1960 or so to present day, showing a steady increase. This is heat content in 10 to the 22 joules, heat content into the ocean, and in this case, there are very few bumps and wiggles. It's a steady increase. Okay, so about 40% of the sea level rise, global sea level rise, is because the oceans are warming. Thermal expansion, the seawater warms up and it gets a little bit less dense and it expands, so that causes sea levels to rise. So we have these effects that not just on the surface of the planet, but also we can notice the ocean is warming. Right. And I think this is an interesting fact. I mentioned it in my last League of Women's Voter talk. I'll mention it again. Recall that Anne-Marie said that what greenhouse gases do is they trap incoming solar radiation. They don't let all of the heat out, okay? So if you actually calculate how much heat is being trapped by the excess greenhouse gases, and then take 90% of that, the part that's going into the ocean, and ask how much energy is that, okay? Some huge number. Well, it turns out that huge number is 10 times as much energy that humans use for everything over a course of 1 year. For every single thing that all humans on the planet do together, think of that huge amount of energy that's used. 10 times that is what the ocean is taking up, you can say, on our behalf, right? And sequestering into the deep. I just think that's an amazing statistic. All right. So what's going to happen in the future? Greenhouse gas emissions from human activity. Anne-Marie did a great job showing the trajectory of carbon emissions and CO2 levels in the atmosphere since Keeling, and even some before Keeling, I think. So what scientists do to make a projection about future climate change is we have to make some what we call scenarios. Okay, so we assume that basically we do 4 scenarios. Okay. And the 4 scenarios are drawn here as different colors. So we have a blue line, orange line, brown line, and a red line. And those 4 scenarios represent 4 different ways that humanity can deal, how humanity will decide to change our emissions over the next 100, 200, 500 years. Okay? And in addition, there are a lot of little lines around it. The little lines are because we don't know how the land will respond, we don't know how the ocean will respond. There are a lot of factors in the climate system that we don't know. That's what Anne-Marie and her colleagues are studying. What's the changing, how will warming soils, how will that change their uptake or release of CO2? So we don't know. But we have these 4 scenarios. The numbers, the RCP, they call it representative, now I can't remember what it is, I'm sorry. Carbon projection, yeah, I forget, I'm a numbers guy. I'm a numbers guy. Representative climate projection, that sounds right. Excuse me. So this number 8.5, 6, 4.5, 2.6, that number, this is what matters to me, is the amount of the imbalance of solar radiation that we expect. So currently we're about 1 watt per square meter. That's the excess heat from global warming. In RCP 8.5, that's 8.5 watts per square meter, excess heat being trapped to the surface of the planet. What does that mean? Well, by 2100, an RCP 8.5 scenario has a global warming expected values of 3 to a little bit more than 5 degrees centigrade. Right now we're at about 1 degree centigrade, plus 1 degree centigrade, a little bit more. So this would be 5 times as much global warming by this scenario. And so these different other scenarios, there's only one scenario, this RCP 2.6. This is the scenario that assumes that we get our act together, that we immediately drastically cut our fossil fuel use. And even more, if you notice, this is a line here of 0 emissions. It goes below the line. So how do you have less than 0 emissions? That's through policies that actively take CO2 out of the atmosphere. Okay, we'll talk about that a little bit more later. But for example, as was mentioned, planting forests would be one technique, right? Or sequestering carbon into the ocean or into deep reservoirs. There's only one scenario that has negative emissions, and even this scenario has global warming 1 to 2.5 degrees centigrade. So in the best case scenario that humans, and we're very optimistic people, that we come up with, we still have about twice as much warming as we have already experienced. And it requires immediate dramatic cuts. So this red curve, like I said, kind of like the worst case scenario, where are we? In 2017, the estimate from the Global Carbon, help me out here, project, GCP, they came up with a number that said we're at just under 40. So guess what? We're on the red line still. We're doing a great job. We're tracking that red line really well, which means that the scientists had it right. This is what it means. This trajectory is if we do business as usual, if we do essentially nothing. So that's what we're doing. That's where we're at. So now I'm going to do some scary things and show you what the world will look like if we get the RCP 2.6, if we do the most stringent reduction, right, the best case scenario, and then kind of the worst case scenario. I also want to point out at this time that the IPCC report is a consensus document, and what that means is that when I say worst case scenario, I mean this is what everyone in the room agreed was the worst case, but not everyone thought that, some people thought it would be much worse. Right, but they weren't in the consensus. So actually, it's a minimum bound. It's bounded by the most conservative voice in the room. Not that I personally have insight about how much worse it can be, but I just want you to know that IPCC upper bound projections are consensus numbers. Okay, so this is the projected change of average surface temperature, and you see, like I said, that between 1 and 2 degrees centigrade is the map with enhanced warming over the poles And in the worst case scenario, this is 9 to 11 degrees centigrade warmer, also with enhanced warming over the poles. That is actually frightening to me. The change of average precipitation, I point this out because we live in Southern California, right? And for us, this is a kind of a perennial issue. It's a little hard to see, but in both RCP 2.6 and 8.5, Southern California experiences between 10 and 30% less precipitation on average. This doesn't say anything about the frequency of droughts, right? So this is just on average, but of course, many scientists think that the frequency and duration of droughts will increase also. To the previous talk, you'll notice that there's in the RCP 8, there are big changes planet-wide of the amount of precipitation. That has actual consequences for how much those parts of the world will take up or release carbon dioxide. So that's why we need OCO2, OCO3, OCO4. We need to understand how, even today, small changes in precipitation impact global carbon stocks. Because again, as scientists, we want to make these projections, right? And right now, we know virtually nothing about how these kinds of changes of precipitation will affect the cycle of carbon in the climate. Average sea level, this is a favorite topic of mine. We're looking at between a third of a meter and a meter in the consensus document. We'll talk more about sea level in a little bit. So now, I was specifically asked to talk about polar ice tipping points. It wasn't in the title. I was asked to talk about it, and when I read the request, it specifically talked about ice sheets. But in fact, there are several polar ice tipping points. So I took the liberty to talk about more than one. and I even left some on the table for the purposes of time. But there are many polar ice tipping points. The first one, which is, before we get to it, let me orient you, right, to the parts of the planet that I spend most of my time looking at, the top and the bottom. Usually on our globes at home, there's a giant stick coming out of here, so we don't even get a good look often, right? All I do is make all these maps all day long, so this is to me very intimate territory. But what they call here is the cryosphere. This just means the frozen part of the Earth, right? The part that has ice. Of course, not everywhere on Earth has ice, but it turns out a huge amount does. So I want to just walk you through the different parts of the ice. The first one is easy, is the snow line. It's here, this kind of black or green curve. It reaches all the way down, right? It snows here. It snows in the St. Gabriel's, right? It just in the snow. Even in Pasadena, I haven't been that. Not yet. It snowed in Egypt recently. It snows in Italy. It snowed in Rome this year. So the snow line is actually almost over everything north of, say, Mexico, and just barely touching North Africa. Okay, beyond that, the next kind of thing that we see in the cryosphere is the permafrost. This is between 1 and 1,000 meters of ice. Sorry. I'm so sorry. I apologize for the YouTube people who are watching this later. Between 1 and 1,000 meters of ice that is below the tundra. Right? It can be ancient ice. It could be millions of years old, at least from the last ice age. And we don't, you don't see it because when you see the nature of documentary, there's just reindeer walking across it. But below that is a huge amount of ice that's trapped. And then the next kind of thing we see is the ice sheets, we have two major ice sheets. We have Greenland and Antarctica. And we'll talk about those in a little bit more. Greenland, of course, and Antarctica, hard to make out on this map. It's about there. There are also glaciers that are not connected to the ice sheets in the Himalayas and the Alps and Patagonia and Canada. But the biggest ice, the most ice trapped on land is in the ice sheets. And the last part is the sea ice. Sea ice is frozen ocean. In the break, I was approached by one of you guys who have actually been to the Arctic and have seen the sea ice in real life. I did my PhD on sea ice. I have never seen sea ice. I have seen lake ice. I've gone ice skating. I've been in fjords in summer that were so full of icebergs that if I squinted, I could pretend I was on sea ice. But I still have I've never been there. That's crazy, right? So sea ice makes up tens of millions of square kilometers in the Arctic and around Antarctica. It has a seasonal cycle. In the winter, the sea ice expands dramatically. In the summer, it retreats dramatically. This yellow line shows approximately the limit, annual average of where the sea ice is. It's pretty huge. So those are the four components. All of those parts of the cryosphere have, you can say, polar ice tipping points. They're all, let me get into it a little bit. So the very first part of the cryosphere we'll visit is the sea ice. And there's this very central concept in climate science called the sea ice-albedo feedback. Sea ice-albedo feedback. It's very simple. It's very simple. It's one of the examples of a positive feedback. Anne-Marie mentioned this idea before. The idea is that you have a chain of events, and each step in the chain of events leads to more of the same. So in this case, let me orient you. This graphic is meant to depict, this is Alaska and Siberia. This is sea ice, kind of looking, North Pole will be around here. And this is a graphic that's meant to show you that sunlight comes in, and about a quarter of it is scattered by clouds, goes back into space. And about a quarter of it, you could say, is absorbed by the atmosphere. And then you have, so the remaining half goes down, and it can either hit sea ice or hit open ocean, the non-frozen ocean. And if it hits the non-frozen ocean, about 90% of it is absorbed. The ocean warms up. If it hits sea ice, it's just the opposite. About 10% of it is absorbed, 90% of it reflects back into space, because the sea ice, think about it, sea ice in general is very bright, right? You have to wear sunglasses when you go skiing, sunblock under your eyes. It's because the sunlight is bouncing off of it, right? It can cause you sunburn. So what happens if the climate, this is a little hard to see, if the climate warms up, that's the first step in our positive feedback, climate warms up, then Arctic sea ice melts. And then, where you had a lot of ice and a little bit of ocean, now you have the reverse situation, a lot of ocean and a little ice. Now the sunlight comes down, and instead of almost all of it reflecting back, almost all of it is absorbed by the ocean. So the ocean warms up. Ocean warms up, the whole balance of the, I guess it gets darker. More sunlight is absorbed, and temperature goes up even further. So there's this concept that maybe we could reduce the sea ice so far, so we could reduce the sea ice to such a point where this feedback will just take over, and we'll lose all the sea ice in the summer. We'll lose all the sea ice in the summer. And I think I have a plot. Oh, okay, yeah. Well, I'll get to it. Oh, sorry. Yeah, I do have a plot, but in two slides. We'll lose all the sea ice in the summer. And some scientists study this and think that, some fraction of that, remember that curve I showed you earlier of the loss of sea ice? Some fraction of that can be attributed to this feedback operating. And this feedback, although I learned it as sea ice-albedo feedback, it also operates for ice sheets. And you can say also snow, right? So if the ice sheets warm up, they begin to melt. As the climate warms, we have longer summers. And also the altitude at which the glaciers, the total area of the ice sheets that do melt in the summer goes up. And when the ice melts, the water, some of it stays on the surface. And it makes these pools. Okay? They're called melt ponds. The water doesn't just always drain into the ice. So that liquid water pooling on the surface of the ice actually is just like the ocean. It absorbs more sunlight. So it's also the ice sheet albedo feedback and the snow albedo feedback. But I just wrote it as sea ice feedback. This is what I think sea ice looks like. Like I said, I've never been there. On a normal cold day. But this is what a lot of the Arctic looks like now in the summer. It's a lot of water. You can't go swimming here. It's just a couple inches deep. Cold. Right? It's cold. Number one, unless you're in the Sierra Club polar bear team. But this is just a huge area where the meltwater is collected on the surface. And this is the plot I want to show. And that's why many scientists think that we will pretty soon lose all of our summer sea ice in the Arctic. So here, these two colors are those two scenarios I mentioned. The blue scenario is the best case scenario, the RCP 2.6. In the RCP 2.6 scenario, we continue to lose sea ice in the Arctic until about 2050, and then we stabilize. And in every other scenario, we lose all the sea ice. 20 to 40 years from now, you can just kayak across the Arctic in the middle of summer. Pretty incredible. Next feedback is one that I think is very interesting, and we read about it more and more in the news. I just saw an article yesterday about this very topic. Permafrost methane or / CO2 feedback. And actually, Anne-Marie mentioned it, or kind of alluded to it earlier. So this purple area is the area of the planet, of Northern Hemisphere, that is permafrost. About 1/4 of the Northern Hemisphere land has permafrost, which is incredible. Anyway, why does the permafrost matter? Well, permafrost, in the permafrost is organic material that could decay and through different organisms that respire, right? They inhale oxygen and exhale carbon dioxide. So right now, that's one reason. So right now, those organisms that would break down that organic material, they're inactive most of the time because they're frozen. The plant material is frozen. So as the tundra and the permafrost melts and the season gets longer, their activity, they're active more of the year, and they can act on more of the plant material that was once frozen. So as they do their decomposition, they exhale, and more carbon dioxide and methane go into the atmosphere. That's a positive feedback. More active, more respiration, more CO2, more methane in the atmosphere. Now we have more melted permafrost. Also, there are natural reservoirs of methane under the ground. And those natural reservoirs of methane, they bubble up. And they get trapped under this ice, under the permafrost. And when the permafrost goes away, well, there's nothing to stop that methane now from just outgassing into the atmosphere. That's another way it happens. So we have a few ways that melting permafrost can further accelerate global warming. And there actually is a lot of research being done right now to try to just get a rough idea about how big this problem could be. Because, look how big this area is, and how difficult it is to go to these kinds of places and take those kinds of measurements. There's actually a mission at JPL that does just that. Actually, a couple. And I'm guessing that the OCO2 to OCO3 will be part of the solution to this answer. Okay. Oh, so I got these nice pictures. I've never seen permafrost either. So here you go. Here is what you would see in the David Attenborough film. It would be this part, and there'd be reindeer, and it would be really lovely. But if somehow you were to do a cross section, you would find ice, literally ice, right beneath it. And this is a case where I'm guessing this big chunk of the permafrost melted. And of course, it's water. You have this huge amount of water being released, and it starts to run downhill, creates a river. That's what we have down here. Melted permafrost pooling at the surface. This is an area that was once completely frozen below, and now it's melted. So there you go, second ice tipping point. The third one I'll spend the most time on is what we call the marine ice sheet instability. It's very interesting, a very interesting process, the marine ice sheet instability. So first, I just want to give you remind you about how the ice sheets work. Okay, ice sheets are a dynamic part of the climate system. They are the last remnants of the most recent ice age. It's hundreds of millions of cubic kilometers of ice frozen on the surface. But they're renewed by snowfall every year. So snow accumulates at the surface of the ice sheet. And it creates a big mound. A lot of snow piles up. It compresses on itself. It becomes ice. And then the ice actually flows, because of gravity, downhill. It flows very slowly, but it flows downhill. In some places, it flows down and it reaches the land, right? By the time it reaches the land, it's all melted, and we don't care about that for this talk. In other places, it flows down, and it eventually, as it flows down, it thins out, and eventually it gets so thin that it begins to float and form these giant, what we call ice shelves. And I'll show you a map of where they are in a minute. This giant ice shelf. So when you have this ice sheet and you have this ice shelf, in Antarctica at least, almost all of the melting of this ice sheet is because of the ocean. Because even in the summer, around Antarctica, it's very, very cold. It never really melts, thank you. It never really melts. So almost all of the melting takes place in what we call the ice sheet or ice shelf cavity, in this giant cave that's formed beneath the ice shelf. Okay, so that's kind of in equilibrium. And in a climate that's stable, this is what it looks like. Okay. Now, this is a map of Antarctica, and there's a color. I colored all of the major ice shelves and try to give you a sense of how big they are. And in case you don't know how big Antarctica is, it's 1.5 times the size of the continental US. So if you put a map on it, it would be Maine over here and California over here. So it's that big. So this is about the size of Texas, right? This is an ice shelf the size of Texas. We have these other giant ice shelves. And here's some statistics. The typical thickness of the ice in Antarctica is 1 to 3 miles thick. And if all of the ice in Antarctica were to melt, just under 200 feet of sea level rise. Anyway, these are the ice shelves that I'm talking about. This is the ice sheet and the ice shelves. Now, oh yeah, this is a cool movie for you. This is a movie interlude. This is a map made by our colleagues that show the flow field. The ice flows from the place of accumulation down to the ocean. And this is an incredible piece of work that shows from observations, just incredible if you think about how it's done. The tributaries, how the ice flows, the patterns of ice flow. It accumulates here, okay, not very much flow, very slow, small gradient, kind of the top of the hill. And as we get closer to the periphery, it speeds up until you get the giant ice sheet. Okay, movie interlude's over. Now, what is the marine ice sheet instability? Well, it's this idea. Sorry, one point before I go any further. The ice sheets are so big and so heavy that they actually, in many places, have depressed the ground below sea level. Right? If you have 1 to 3 miles of ice above you, and you were originally near sea level, it's not hard to imagine that the crust, the Earth's crust, actually deforms under that weight. And now that what they call the bed is beneath sea level. So this is now a schematic of a cross-section of the marine ice sheet and the ice shelf. So here is the ice sheet. Here is the ice shelf, the part that's floating. Here is liquid ocean. This is the cavity. And what we call here the grounding line, this is where, like I mentioned, the ice sheet becomes so thin that it eventually begins to float, right? So out here, it's below sea level. The sea level is about here. It's below sea level, but it's so thick that it doesn't displace more water. It doesn't float. Here it begins to float. So there's this idea of the grounding line, and in balance, the same amount of snow that falls over the surface is what flows out laterally out the side. It's like the bank, as Anne-Marie was talking about, the budget. Same amount is going in from the top as going out the sides. Okay, this is under normal conditions. Same going in as going out. Okay. Now, in what they call the marine ice sheet instability, something very strange happens. Say there is an increase of the melting beneath the ice sheet in the cavity. And I'm sorry, it's not hypothetical. This is actually happening. There is an increase in the melting in the cavities. The oceans are warmer. And what happens is that the grounding line, it retreats. And in this case, it's going into a place where the bed is deeper. It's more depressed. And that makes sense, right? Because it's thicker ice upstream, so there's more weight, it's more depressed. It goes into a place that is deeper. And when it goes into a place that's deeper, the amount of ice that flows out across this line actually increases. It increases to the 5th power. This is some crazy thing if you're a scientist or engineer. To the 5th power of the change of the thickness of this ice sheet. So it really begins to kick out. And what happens is that two things happen. One, the ice sheet thins, and two, the front actually retreats further. So this is what is another positive feedback. You push the ice sheet, you push the grounding line back a little bit, and then it just kind of snowballs, and it retreats all the way back until the bed levels out or starts going in the other direction. So how big of a deal is this? It's actually like an incredibly big deal, because huge areas of Antarctica have their bed below sea level. So this is a map that shows the bed of Antarctica, and everywhere that it's greenish or bluish, it's below sea level. And again, I put this map here to show you. So right now, Antarctica, all of this part of Antarctica that you see as blue, this is ice sheet. And also there's a large area over here. This is called West Antarctica, the West Antarctic ice sheet, and this is the East Antarctic ice sheet. You see over here in this sector of the East Antarctic ice sheet, also a lot of blue. So scientists are actually really, really concerned about trying to figure out whether the ice sheet has reached a tipping point, because the oceans have warmed so much that now the retreat of these ice sheets is unstoppable. And some colleagues of mine have actually gone on record and said, yes, now they have evidence that it has begun and it is unstoppable. And the big question that no one has the answer to is just how fast this process will take place, because there's no precedent for it, of course, in human lifetimes, and only a scanty data from the paleo record. So there's a lot of effort being put into understanding what is going to happen. And I put this map up here to show you, not to scare you, but just to show you that we know it's happening, because these are observations made from a space-based platform called the Grace satellite, which just died, by the way. Just terminated its mission. And it shows since the launch of the spacecraft here in 2002 until this is only updated 2016, but it shows This is the trend of mass in Antarctica, right? Downhill trend. And it shows a map of where the ice is being lost. And you remember earlier I said West Antarctica and a little bit over here in East Antarctica are the places where we're vulnerable to this marine icy instability. It's exactly the same places where we're currently seeing the ice sheet melt away. So it's a really big deal. And why do we care about the Antarctica melting? Well, one of the reasons we care about it is because of sea level rise. With those scenarios, the RCP 2.6, the RCP 8.5, those scenarios each have with them a projection of sea level rise. Right? It makes sense? But the number one factor, the thing that we have the most uncertainty about, is what is going to happen to the Greenland and Antarctic ice sheet. And partly because of that marine ice sheet instability I just mentioned, I just described. So it's a little hard to see, but here on these, so this is a map of sea level rise from 1700 until a projection 2100. This is where we are today. And we have the two curves. Red curve, that's the RCP 8.5. And the blue curve, that's the RCP 2.6. You'll notice that both are clearly going up, right? Clearly going up. And the 8.5 is significantly higher. This is from today. This is what it might be. What you don't see on this chart is just how uncertain it is, right? No scientist is going to bet on either of these lines. Thank you. The envelope for uncertainty is actually really huge. That's why we care. And for the benefit of time, I'm going to skip to the very end of skip that one talk about the catastrophic consequences of sea level rise, because if you don't know about it, you can Google it. Catastrophe. So I was, the end of my talk title is "Prevention is the Best Cure." So I just wanted to mention what some of the, if you don't prevent the problem, you have to go to the doctor. The doctor gives you a prescription. Some of the ideas that people have about fixing the problem without actually getting to the root of the problem. The Band-Aids, we'll call it, right? So Anne-Marie actually discussed this a little bit already. There's this concept of geoengineering. It terrifies everybody. Even the scientists who look at this are not not big promoters of it, but as scientists, we study it because we want to know what our options are. Okay? So there are two really high-level categories of geoengineering. One is to reduce the amount of sunlight coming onto the planet. I know, right? I know, everyone freaks out at this point. And number two is to somehow remove the CO2 from the atmosphere. So the first one, it sounds terrifying. The second one sounds like, yeah, everyone can get behind that one. While I was preparing for this, I actually found there's a board game called Geoengineering. $39. It sounds super cool. I'm going to get a copy. And they have a section, how do you win? How do you win the game? And this is what they wrote. A world where climate change has gotten so bad that geoengineering is on the table is one without winners. Only those that lose less. I think that is a perfect encapsulation on how people feel about geoengineering. Yeah. So your options of this game they actually match up really well with what people talk about today. But there's one category of thing you can do, which is like industrial sabotage. So, yeah. Definitely not promoting that, but that's an option. So the first category of reducing the amount of solar energy. So I think people break it down to four areas. And I picked benign figures for you guys. So you would just think, yeah, okay, this is not so crazy. First one is to make the surface of the planet lighter colored. Right? Well, it's like the Ice-Albedo Feedback, but in reverse. Right? You want a light that comes down, you want more of it to bounce back. We already do a lot of human activity is doing the opposite now, right? Like asphalt is a lot darker than sage, right? So we already are geoengineering our way in this area in one direction. but we could make our roofs brighter. And one idea which I didn't know about, there are people who are advocating that we kind of change what crops are planted. Because you could have wheat, and different strains of wheat can have different brightnesses. Some plants are just brighter than, some varieties are brighter. And a huge amount of the surface of the planet is agriculture. So we could gradually change what's planted to make it brighter. That doesn't sound so bad. The other idea is this thing called troposphere brightening. And Anne-Marie mentioned it. The idea is that you basically would create these vessels, and the vessels would pump up seawater into the atmosphere. And the salt basically the salt, CMS, in the seawater acts as a condensation nuclei. Basically, it seeds the clouds. So it's a natural way of creating more clouds. And the clouds that normally form over the ocean, they're very bright. So you could imagine a fleet of these ships cruising around, pumping up seawater, right? Creating the cloud, and then the clouds go away. It's not that crazy. Clouds go away, and as you've done that, you've now, over the period of the course of that cloud, you've made the surface of the planet brighter, and more sunlight is reflected out into space. So it's one of the ideas. Another idea which nobody likes, I think, and Anne-Marie mentioned it again, is the idea of pumping aerosols into the stratosphere. So you can do it by planes. In this concept, there's a ship with a balloon, and the balloon is very high, and you would kind of shoot out aerosols into the stratosphere. And do you remember the idea of the nuclear winter? Remember that? So it's like a mini nuclear winter that we do to ourselves with the hopefully less catastrophic everything freezing. It's more like the aerosols act as scatterers, and sunlight is reflected back into space. And the plus side is that this aerosols, they don't live up, depending on the size of the aerosol, they could be short-lived, they could be long-lived. You have to do it continually because they keep falling out. Nobody really knows what the environmental consequences would be. But a lot of people do actually study if it'll work in climate models. So that's interesting. Yeah, I know. And another far-out idea is the space-based mission, where you put a giant mirror, or in one case, one person suggested trillions of mirrors, very small ones, in certain places in the L1 point, and that will just directly scatter the light coming from the planet. These are more far-fetched because it would basically be like the entire human space effort and industrial effort would go to creating these missions. I'm going to wrap it up. I got only one more slide. The CO2 removal from the atmosphere, planting more forests, using what they call bioenergy. So you burn the fuel that you've grown. That's carbon neutral, more or less. Carbon capture and storage. Through chemical means usually, you trap the carbon coming out of the smokestack. It's in a highly concentrated form. It's very efficient to deal with it then. You pump it into the ocean, or you pump it into deep reservoirs in the ground, maybe former oil wells. Actually, my office mate in graduate school worked on this project, and the only reason it hasn't gone anywhere is because there's no tax on carbon. There's no incentive for industry to do this, because it doesn't cost anything to put it into the atmosphere, approximately. Last idea is ocean fertilization. For the interest of time, I'm going to skip it. So now, prevention is the best cure. That was in my title of my talk. This is a quote from the IPCC. Limiting climate change requires substantial and sustained reductions in greenhouse gas emissions. Right? That is the bottom line. Probably not engineering our way out of this mess through the techniques I just described. Substantial and sustained reductions. Greenhouse gas emissions, which together can limit the risks. So people always ask, what can you do? What can we do? Right? And I think there's a lot we can do. And being here with you all today makes me very hopeful. because obviously everyone in this room cares about this subject. We've come here on a Saturday morning, beautiful day for hiking, right? The Sierra Club people, I'm very impressed that you're here and not on the mountains. What we can do, number one, we can vote, right? Now, don't just vote for anybody. But this is, I think, number one, because the scale of the problem is requires organized international action. Number two, promote climate literacy in your home and community. This is probably the most, I think of all of these, the most important, because unless children know about this problem, if they're not taught it in school, then what are they going to do, right? They're the next class of voters. Educate yourself about your own carbon footprint. There's a lot of websites and books you can read. Just like, going on a diet, You grow up in a house, everyone just eats cake all day, and eventually you grow up and you're like, wait a minute, cake may not be the best thing to eat. Let me learn more about cake and nutrition. And once you know about it, once you know a little bit more about nutrition, you can start making some informed choices. So I bet most of you, because this is what my experience, most people who even care about climate haven't calculated their own carbon budget. It's not a scary thing to do, right? Because we're probably not that high, people in this room. We're probably very conscientious people. But it's worth doing, right? To see how much is my driving, how much is my heating, and just to do the budget. Because you can easily see, maybe it'd be really easy for me to make a small change of my life, and it'll have a big impact on my carbon footprint. This one turns out to be very important. Adopting a plant-based diet, a more plant-based diet. It's sad but true. I don't want to sound like very preachy, but a vegetarian diet or a vegan diet has a huge impact on your carbon footprint. Like probably the easiest, number one thing you can do to reduce your carbon footprint is have a meatless Monday, right? Also, I have to point out, and I've lived in a lot of different places. LA is like besides Portland, Oregon, LA probably has more vegetarian and vegan restaurants anywhere in the world. Just go to them occasionally, right? And it will have a big, measurable impact on your carbon. I've been a vegan for 20 years, and I'm fine. I'm fine. Stay positive. Thank you very much. Last thing, I want to make a shout out to there's a new website at JPL, climate.nasa.gov, and it's a great place to learn about NASA's measurements of the climate system, and it's a really great website, very easy to get into and read and learn more about the subject. So I encourage you all to go to that website too.
Just take it for a second. We're running a little late, but that's all right. I didn't want to cut off the speaker in his last few slides. We'll have Q&A, and if we need to, we can go a little over 12 o'clock, no problem. If I don't get a chance to do it later, I want to thank everyone for coming, for the people who helped put on the forum, for the people who have come to see it, and particularly the speakers, Anne Marie and Ian. We're very appreciative to have them give their excellent presentations. So don't forget, after the Q&A, please fill out your questionnaires and turn them in. It shouldn't take very long. We'll go ahead and do the Q&A now. Thanks. Please line up in the center aisle.
Very short one. I believe I heard in the media that although the melting of glaciers in Greenland has resulted in some sea level rise, that actually the sea level rise is less off the coast of Greenland than in other parts of the world. Maybe you could explain that if you're aware of why that would be the case.
Oh yeah, I do know the answer to that question. It's an incredibly interesting topic. Greenland and Antarctica store so much ice that they actually they have their own gravitational pull on the oceans. So everyone who's had gravitational physics knows. Everyone knows this. Come on, that everything that has mass, it has some gravitational attraction to it. So Greenland and Antarctica are so big that they basically attract the ocean towards it. That's normal. If you look at the shape of the ocean, it kind of bulges up towards Greenland and Antarctica. But what happens is that as the ice sheets melt, the mass of those ice sheets goes down, the strength of the gravitational pull goes down, so the ocean is less pulled towards it. It relaxes back down. It lowers around it. It's not pulled up as much, and now it's a little bit lower. So actually, right around Greenland and Antarctica, we expect sea levels to fall. But what goes down around Greenland comes up somewhere else. And some colleagues at JPL have done some really interesting work where they say what cities will be, because of this very effect, what cities will be the hardest hit, what cities will be the least hard. Turns out LA is right in the bullseye of the worst case, because we're far enough away from Greenland and Antarctica that we'll get because the ocean relaxing back to its normal state, it'll be the worst here. So that's the answer. Okay, next question. Come on.
So one of the scariest things of climate change is this delay factor, and you showed it quite a bit because you showed in that optimistic scenario on your last chart that even when most optimistic scenario there was going to be at least another foot rise in sea level, even with a projection where we went negative. And so I'm curious, to me there should be more publicity of this or whatever, but anyways, what is the inevitable sea level rise, even if under this optimistic scenario?
Thank you for the question. I actually almost included that graph from the IPCC. So the short answer is that nobody knows what the worst case scenario is, because even RCP 2.6, we don't know how the ice sheets will respond. But even if the ice sheets do nothing, if they don't contribute at all, sea levels will continue to rise for hundreds of years. Because when we stabilize our CO2 levels in the atmosphere, they'll inevitably be higher than they are today. But even if they were the level they're at today, the oceans are not in balance. It's a huge amount of time to warm up the oceans to get them to be in equilibrium with what the atmosphere is doing. So for hundreds, actually thousands of years, the oceans will be warming up just to get to where they are today. And as they warm up, sea levels will rise. And how much that will be, I didn't include the chart, and I don't keep the number in my head. But I would say most of us are thinking about the 8.6, the 8.5 scenario more than the 2.6 scenario. But yeah, that's a good point. Even if we stopped all emissions today, sea levels would continue to rise for over 1,000 years. Sorry.
Hey. Okay, so this is just kind of a personal question. It's something I've been wondering about for a really long time. Doesn't have as much to do with sea ice.
Oh yeah, they're recording it from this microphone.
Okay, so you've got a great big megalopolis like Los Angeles, big world city, 18 million people, what have you, and you got a great big megalopolis at a much higher latitude. I'm thinking Puget Sound. Lots and lots of millions and millions of people, and I just wonder in terms of all the emissions that come from a great big world megalopolis like that, each of these two, which one is more? Is it possible that the one at the higher latitude has a more damaging effect on global climate change and warming and all that kind of thing?
It's a good question. I think Anne Marie probably is the expert on this, but when I think of CO2, I think of it as what they call a well-mixed greenhouse gas, which means the atmosphere has its own circulation, right? You put something in the atmosphere here, it's going to, over a decade or 2 decades, become pretty well mixed across the entire planet. CO2, it has its what they call the residence time. It's like 1,000 years, like a couple hundred years residence time, which means that you can expect, on average, that it'll take a few hundred years for, like the E-folding time, a few hundred years for your CO2 to come out of the atmosphere. So I don't think it really matters where the emission takes place, because pretty soon the greenhouse gas will be mixed throughout the entire atmosphere, and that's it. That's how Keeling was able to make, we're showing these Keeling curves. Keeling's measurements were from Hawaii, one spot, right? So how is it that we were able to get these measurements and believe them for the for Earth CO2 from this one spot? It's because greenhouse gases are pretty well mixed. If you pick an area that's away from a tailpipe, away from industry, and that's what this site in Hawaii was, right? The air coming over that site came over the Pacific Ocean. So it's clean air, not directly impacted by local emissions. It's representative of the whole planet. We still need to map put measurements everywhere, but it doesn't really matter where the emissions come out. Yeah. Good question, though.
Two small question and a personal question.
Oh, sorry. Stand in front of this microphone, please.
Okay, small question and a.
You have to do both.
You have to do both?
Yes.
One of them is going to work. The small question is, I've read that soot from.
Hold that close.
I'll just shout.
Hold this closer because they're recording that.
Okay. Okay. I've read that soot from dirty power plants in China and Asia, and fires ends up landing in the Arctic and changes the albedo of the ice. Has this the significance of this, and then the move to maybe try to clean things up? Is this something we should be doing as fast as possible? Is it really worth considering? And then the other one is on a personal level, how do you deal with this?
I'll answer the first question. People study this issue as darkening of the ice from soot. On the whole scale of the melting of the cryosphere, I don't have a sense of where it falls. Locally, it can be important. There are places on Greenland, for example, and Canada, people can collect the soot and they measure it. It does darken the ice, so it's part of this feedback, right? If you darken the ice when the melt season begins, then you can pretty much bet by the end of the melt season you will have melted more ice there than if you started with clean, pristine ice or snow. So it's part of the issue, but I can't give you a sense of how big in comparison. Second question for how do I deal with it on a personal level? I think my personality is pretty optimistic. I'll put it this way, it's self-selecting. If I were prone to despair, I wouldn't have made it to talk to you today. I don't know the true answer, but I am hopeful because we got into this mess. I think we can get out of this mess. And with smart people who put in the time and put in the effort and come to events like this and work in your communities, I think we can get out of it.
So I'd like your input on, recently scientists have said that the melting and the fresh water going into the oceans, the melting, especially from Greenland and Antarctica, is already affecting the ocean circulation, the AMOC, the Atlantic Meridional overturning circulation.
That one I know.
So I want your input on that, and is it serious, and what are the consequences of it?
Potentially serious. There's a lot of, it's an idea that's been floating around for a long time, that if the ice sheet, especially Greenland, if Greenland melts and all of this fresh water makes its way into the ocean, because that's where it goes, right? And that fresh water is very buoyant, right? It doesn't have any salt in it. It's very light, so it can create like a layer on the surface of the ocean. And what happens is that in the wintertime, normally, if the ocean water is not particularly normal ocean water in that part of the world, it gets dense when it gets cool. It cools and it shrinks. It gets denser and it sinks. Okay, so this it's kind of hard to explain in short notice, but it sinks, and the water that sinks becomes part of what we call the global overturning circulation. So, I think for us the most important thing is that sinking water, it also brings it also sequesters CO2. So that's kind of like, for me, that's the most important part of it. And so if all of this fresh water pours out, melts out, and spreads out over the North Atlantic Ocean, then in the winter there won't be so much mixing, there won't be so much, so you can say, sequestration of the carbon into the deep waters. Also, the extent of sea ice will go up, because the ocean could freeze on very fresh water on the surface. That's why the Arctic is covered in sea ice, because there's a lot of river runoff, a lot of fresh water. The surface is not very dense. It can freeze. It's pretty interesting, actually. So it could happen, and it has happened in the past, that huge areas of the North Atlantic have been frozen in the winter. So that's one issue. As to the likelihood of it happening, I can say it's an area of active research, but not a subject that keeps me up at night. Yeah.
Not really a question so much, but I recently read about the city of Los Angeles is going to be painting 40 miles, I believe, of their asphalt streets white. A very expensive procedure, but they're talking about how that'll help reflect, and it'll also keep the buildings cooler. You know anything about that?
I don't know about that plan in Los Angeles, but it is exactly the right kind of plan. Because in cities, because we have all this asphalt and this, we're disproportionately affected by the heating.
Yeah.
Called the heat island effect. So there are a lot of health consequences to being subjected to that kind of temperature.
Yeah.
Also, if it's super hot, you want to run your AC more. Then that creates, more energy is consumed. That's another feedback that people don't really talk about. So the idea of keeping the city cooler has benefits for everybody, locally, regionally, and for the planet. So I think that's a great idea.
Yeah, the cost they said was huge, but they feel that the net cost will be very, very beneficial because of those benefits.
Thank you for sharing that. I didn't know. Yeah, thank you. Okay, thank you guys very much.